Okay, so what we're going to be doing today is we're continuing on with chapter 2. So this is day 3 on chapter 2, just to give you an indication of how crucial this chapter is. And today we're going to be taking a look at variance and the standard deviation. So we just finished up our look at measures of central tendency. Now we're going to be taking a look at measures of variability, variance, and standard deviation. And the reason we're doing this is because we want to be able to summarize our data effectively, and oftentimes the mean, the measure of central tendency, just isn't adequate to accomplish that. So I'll give you an example of where you could lose important information if you only considered the mean. So let's say that you were running a clinic, and in this clinic you treated people with depression, and you had people with 2 different types of depression. So we have 2 different types of depression, and you know that if somebody has a very high level of depression, then your policy is you need to put them on suicide watch. You need to put them into a safe environment where you know that they will not harm themselves. And you know that this is only going to occur for people that are very high on scores of depression. So let's say that you take your people with depression A and you take your people with depression B and you measure their depression on Beck's depression inventory. And for group A, we get an average score of 42.6, and for group B, we get an average score of 25.7. From this information, you would conclude that group A has more people in the high depression area. Group A has more people that need to be placed under suicide watch to make sure that they do not harm themselves. And in this situation, you would be completely wrong. Because while the mean is giving you a good indication of the distribution, we need another piece of information. Specifically, we need to know how spread out are the scores. So it could be that group B, their mean is right there. Beck's depression inventory score of 25.7. Group A, their mean is right there. They have an average score of 42.6. And that area right there, that is suicide watch. That is where, if anybody falls into this area, they need to be placed in that special, protected, safe environment. So how many people from Group A are going to fall into that danger area? Well, as it turns out, nobody. That's the frequency distribution for scores from Group A. And as you can see, the mean is 42.6. That balance point is right there at 42.6. But the variability, the spread of these scores is not very high. So no scores fall into that suicide watch. For Group B, however, even though their mean is less, their scores are way more spread out. In which case, they are the only group that has anybody that needs to be placed into this special safe environment. So in order to understand the distribution, we can't take a look at all the numbers, right? That's why we're doing these descriptive statistic strategies. But now we're going to add one more number today that gives us a better understanding of the distribution as a whole. We have a measure of the center of the distributions. Now we're going to take a measure, we're going to get a measure of how spread out these distributions are, and that is variability. So we're going to take a further look at our introduction to variability. We are then going to just highlight, foreshadow the importance of variability to inferential statistics. Inferential statistics being the latter half of this semester, the cool ninja stuff that we are going to be able to do. We're going to take a look at how to calculate the 2 major measures of variability, standard deviation and variance for population. We are going to see for the first time ever that those functions are different for samples, and then we're going to have time for some in-class follow-along practice and extra practice, and at the end of today, you will be ready to do homework assignments 3 and 4 because they ask for measures of central tendency and measures of variability. All right, so introduction to variability. So let's consider the following frequency distribution. So we have this frequency distribution right here, and it has a population mean of mu. So there it is right there. That's the balance point. And hopefully when at this point when I say, oh, look at this frequency distribution, you are immediately understanding possible scores. Height of the bar or height of the line is the number of people that had that actual score or achieved that actual score. So we can see that this frequency distribution here has a mean of mu, has a population mean of 100, and we can see that this completely different frequency distribution also has a mean of 100. So we need a way of capturing the difference between these two distributions so that we can make those types of, we can understand these distributions without having to understand all the numbers. So as it turns out, we need one more number, and this is the number that will tell us about variability. So variability, this is a measure of how spread out the scores are in a distribution, how different scores are from each other in a distribution, basically how much variability is there in any particular distribution. If there's low variability, everybody is basically achieving the same scores. If there's high variability, people are achieving very different scores in your distribution. So what we need, though, is we need a way to quantitatively describe how these distributions are spread out. So it's not enough as a psychologist to say, oh, these scores are very variable, and these other ones are not so variable, but these other ones are very, very variable, right? We need numbers to this so that when we communicate, we can be very clear and everybody can agree. So we're going to see how to get numbers on that. And this is going to become extremely important. Everything that we're looking at, frequency distributions, measure the central tendency, now variability, those are all building towards our ability to do inferential statistics. And variability is going to come into play, and it is what gives you, it is part of where the power of inferential statistics comes from, and I'll show you that with this example right here. So let's say that we have two samples, sample A and sample B, and let's say that sample A is, let's stick with depression, let's say that sample A is people who are depressed and they received drug A, and sample B are people who are depressed and they received drug B. And what we would want to do is we would want to know, is there a real difference between the effectiveness of drug A and drug B? And what inferential statistics does is it takes a look at basically how far apart are those distributions? How much of a difference is there between the scores of sample B and the scores of sample A? And in this case, it is pretty easy to see that scores of sample A over here are lower than sample B. People in sample A have lower amounts of depression than sample B. It's pretty easy. We can even see this just visually. We don't need statistics to conclude that drug A is a better drug. But what happens when that overlap is not as evident? Well, what happens is it gets more difficult to tell if the samples indicate that the population is different. It gets more difficult to generalize from your samples to your population. And the more overlap there is, the less likely you are to actually detect a difference. So inferential statistics takes into account the overlap between two samples. And the more overlap there is, the less likely you are going to be able to detect if your drugs are differently effective. Overlap is one of the keys, and that's why variance is so important, because you can either find a difference because your differences are very large between your measures of central tendency, or you can find a difference because your variability is very small. So here you wouldn't be able to find a difference, but as these scores get squeezed together and as the variability goes down, notice that the distributions are no longer overlapped, even at this very small amount of a difference between the samples. So inferential statistics takes the distance between samples and their variability into account, and that's why we're going to dedicate today to understanding that measure of how spread out your scores are. All right, any questions so far on the general idea? All right. So, standard deviation and variance for a population. We're going to start off with a population dealing with all the scores from everybody that fits a category. So a population literally means everybody. If you're talking about the population of university students, you're talking about every single university student on the face of this planet. If you're talking about the population of alcoholics, you are talking about every single alcoholic on the face of the planet. In psychology, you very rarely ever deal with populations. I have never seen population data in my entire career as a psychologist. However, you're always trying to help the population. So you want to take what you know about a sample of alcoholics and say, oh, this treatment that I found can help the population of alcoholics. That's where stats gets its power. So we're going to start off with standard deviation and variance for a population for the sole reason that it's mathematically easier. And that's it. We hardly ever deal with populations, but it's just easier to understand what we're doing when we start with a population. All right, so we have a population mean, we got a population distribution. The first step that we need in order to measure variability is the idea of deviation. And what deviation is, it is the distance from the mean for any score in this population. So every single score in this population has some deviation. It's got some distance from that center line, that population mean. So that person right there, they have a deviation, they're not on the mean, and they have positive deviation, right? So they're above the mean. Their deviation is positive. That person over there has a smaller deviation. They're closer to the mean, but their deviation is negative. They're on the other side. This person from the population has a very large negative deviation. They're way below the mean. Means all the way over here, they're all the way down here. There's very few people with a deviation that large. This person over here has a very large positive deviation. And then this person over here has a deviation of 0. They happen to be right on the mean. The mean for this population is 100, and this person's score is also 100. So that's what a deviation is. It's just the distance from the mean. And you can see that the deviation is a great starting point for building up a number measuring variability. Because the larger the deviation, the more variability in a population. If everybody had 0 deviation, everybody would score 100. There would be no variability. So the formula for this is your score minus the mean. So if you're calculating deviation, it's just the score minus the mean, and you would do that for every single score. So for every single score, you take away the mean of the population, and that gives you the deviation for every single score in this distribution. All right, so that's the starting point. We're starting with deviations. What we want to do is we want to find basically the average deviation, right? So all of these scores are deviations. And if the average distance from the mean is large, that means that your population scores are very spread out. If the average deviation for your scores is small, that means that your population is not very spread out. So average deviation is what we're trying to get at when we're doing variability. However, the mean is the balance point for this distribution. That means that the weight of scores on this side equals the weight of scores on this side. To put it another way, that's to say the size of the deviations on this side are going to exactly equal the size of the deviations on this side, which means that when you add up all the positive deviations and you add up all the negative deviations, you will always get 0. So the average deviation for any population is always 0. So we can't use average deviation to measure the spread because all the deviations cancel each other out. What we need to do is we need to get rid of those negative deviations. And what statisticians did is they said, all right, we're going to square it. We're going to square every single deviation, and that's going to get rid of all of the negative deviations. So they squared all the deviations. They took the distance from the mean squared. So your score minus the mean, and then all of that in parentheses squared, and that's your squared deviation. So that was step 2, get rid of all the negatives. So if you remember our measures of central tendency, if you remember the mean, if you're going to calculate the mean, if you're going to calculate the average, which is what we're trying to do, we're trying to calculate the average deviations. At one point, you're going to add everything up and then divide by the number of scores. And that is our very next move, is the add everything up. So we are now taking our squared deviations, and we're going to find the sum of the squared deviations. And this is the sum of the distance from the mean squared, and this is the sum of your score minus the population mean, and then all of that squared. And you can see where the order of operations is coming in to be very, very important. Now, this is one of the most important concepts in statistics. It's going to come up again and again and again and again. This sum of squared deviations is just massively important. It's one of those moves that is almost done in every single calculation in statistics. And it's so important that it actually became confusing. So if you recall, I mentioned that if a concept has a term, it's because it's incredibly important, right? If a concept comes with a term, it's because it's used over and over and over again. So the mean is used over and over and over again. That's why the mean got a symbol for population. It was mu. The median is not used over and over and over again. That's why the median doesn't get a symbol. It's used median. So to kind of help you think about this, I want you to think about the times before computers. I believe they called them the dark ages. I'm not sure. But anyways, it was the time before computers. Statistics was still being done. And the way that you did statistics back in those days is if you were a researcher, you would collect all your data, you would have a pile of papers about that large, and you would take that paper to the 3 grad students that were part of your lab, you would drop it on their table, and you would say, do statistics. And your grad students would take that and they would by hand calculate all of the statistics. So computer programs back in the day were 3 grad students locked in a tower doing their work. So what happened with these students is that they kept writing things over and over, and this is my version of history, but it's probably true. They kept writing things over and over saying, all right, the mean equals this, the mean equals this, the mean equals this. And they started getting carpal tunnel syndrome. And they said, we can't keep writing the mean. This is way too much. We use it way too often. Let's just use the symbol mu. All right, everybody, mu is going to equal mean. All right, can we all agree? Great. We're going to save our wrists. We're going to save our arms because we're using the mean so often. What happened is they came across sum of squared deviations. And they were like, all right, sum of square, too much. We're using this too much. What do we want to call it? How about SSD, sum of squared deviations? And they were like, that's great. Sum of squared deviations, sum of squared deviations. Still ouch. Still using it so much that even an abbreviation was not enough. So what they did is they abbreviated it again. And instead of SSD, sum of squared deviations, they abbreviated it to SS. All right, that's my revisionist history, but hopefully it'll let you help you remember, because the symbol for this is just SS. And what trips up students incredibly at this point, in a pitfall that I don't want any of you to fall into, is to get tricked by that SS and think that it stands for sum of squares. It does not stand for sum of squares. In your book, they might write it out as sum of squares. When you talk to people, they might call it sum of squares. In other statistical texts, you might read, it might be defined as sum of squares. Don't fall for it. It is not sum of squares. It is sum of squared deviations. So it is not, you gotta be very careful, it's not this. It is not the sum of the scores squared, right? Sum of squares. Oh, this is a square. There's your sum of squares. No, this is not sum of squares. This is sum of squares. So what I want you to do to be safe, anytime you see SS, first off, do not read it as SS. That's the worst thing you can do. SS is meaningless. Secondly, do not read it as sum of squares. Sum of squares is going to program your brain into tricking you into thinking that this is what it is. That's not what it is. Read that SS as sum of squared deviations. Right? Take a moment of silence for those poor grad students locked in the tower suffering from carpal tunnel syndrome. All right, read it out as sum of squared. Pour out your drink on the ground, whatever you need to do. Don't fall for the trick. Don't fall for the trap. It is sum of squared deviations. All right, so this was actually so important and so difficult to calculate that you'll come across this in the text as well. This is why I want you to be aware of it. There's a definitional formula for sum of squared deviations, which is literally you take your deviations, you square them, and then you sum them up. That's the formula, definitional, for sum of squared deviations. What those graduate students did is they actually came up with a computational formula that made it a lot easier and a lot quicker to calculate those scores by hand. So that's the computational formula. I'm only mentioning it here because this is easier to calculate by hand. So if you're ever trapped on a desert island and you need to do some stats, remember this formula. All right, you can grind it into the sand or whatever you need to do. We're not going to use it, we're going to use Excel. So we got programs, we're going to calculate sum of squared deviations in Excel, but just so you're aware, these two are mathematically equivalent. All right, so now we have sum of squared deviations. We started with the deviations, we squared them, we summed them all up. Now we're finally ready to calculate population variance, and what we do is we just take the average squared deviation. We take our sum of squared deviations and we divide them by the number of scores that we started with. So population variance, your measure of the variability of a population, is the sum of squared deviations divided by the number of scores. And that gets sigma squared. So sigma squared, read that as population variance. So that's population variance right there. And this is, again, population variance. This is an important concept. It's sum of squared deviations divided by the size of your sample. But it's not exactly what we wanted, because we wanted average squared deviation. Sorry, we wanted average deviations, not average squared deviations. It would be like somebody asking you, what's your GPA? And you tell them, oh, well, my squared GPA is 10.2. That's my squared GPA. They're like, I don't want your squared GPA. I want to know your GPA. Well, we don't want squared deviation, right? Squared average deviation. We want average deviation. So our last move is to get the population standard deviation, to take this thing that was squared, and we just take the square root. So sum of squared deviations divided by the size of your sample, the size of your population, that gets you population variance. Take the square root of that, that gets you standard deviation. And that is the two measures that you'll see, population variance and population standard deviation, and that gets the symbol sigma. All right, any questions on that? Okay. So that's the standard deviation and variance for a population. We went through that just so you can see the inner workings, just so you can see exactly what is going into this calculation. What we're going to do now is we're going to do the same thing for a sample, and then we're going to go through how to calculate those in Excel. So for a sample, this is going to be the first time where your variance calculation for a population is different than a sample, where your calculation for populations is different than that for samples. So let's start it off. So this is what you're going to be using most often as a psychologist. You're most often going to be dealing with data from samples, because it is technically, literally impossible to calculate data on a population unless you're dealing with the population of people that are so small, so well defined that there's only like 12 of them in the world. All right, so usually we're dealing with samples. And the first thing that we need to appreciate is that samples, by definition, just because of the way that they work, they're usually less variable than a population. If you take a group of people out of a population, that group of people, randomly selected, will tend to be less variable than the population. So just to illustrate why this is, let's say that we have our population there, we have our population mean. So this is everybody, right? This is made up of millions of little scores, creating this entire frequency distribution, including this person over here, who is the lowest scoring person in the world. and this person over here, who is the highest scoring person in the world. And you can take a sample from this population. You can take a sample of 5 people from this population, and they'll have certain deviations from the mean. If you just take a look visually at the variability of this population, you can see that the population is spread that wide, right? It's spread all the way down to the lowest scoring person in the world, and it's spread all the way up to the highest scoring person in the world. Unless you get extremely lucky and happen to choose in your sample the lowest scoring person in the world, and also happen to choose in your sample the highest scoring person in the world, so we're talking 1 out of 7 billion to get this person, multiplied by 1 out of 7 billion to get this person, unless you do that, your sample variability is going to be less than your population variability. So just by the way that it works, sample variability, sample spread is going to be less than population variability. And that's a problem because we want to know things about the population by looking at the sample. We want to estimate the variability of the population by looking at the variability of the sample. We take a look at the sample to say things about the population. So the fact that the sample is biased to be less variable than the population means that we need to adjust our formula. We need to change the formula for sample variance so that it becomes a true predictor of what the population variability is. And this move that we're going to do is something that everybody here is probably extremely familiar with. So the fact that this sample variability does not equal the population variability does not mean that this information is useless. It doesn't mean that it's not worth seeking that information out. It just means that we need to adjust it a little bit to make it useful. And everybody has this experience because everybody, I'm sure, has that one friend that just cannot estimate how long it's going to take them to get ready. And if you don't have that friend, you're probably that friend. So, we all have this one person where you're going out, it's Friday night, you tell them, I'm going to come by, I'm going to pick you up. How long is it going to be until you're ready? And you know that they always underestimate their time. However, you also know that it's not a waste of time to get that information, because if they say 20 minutes, you can tell them, all right, I'll be there in 20 minutes, and you know that you got half an hour before they're going to be ready, right? You just have to adjust their estimate of time. If you call them up and they say, oh yeah, you know what, I started getting ready a bit late, it's going to be an hour, you're like, okay, great, I'll see you in an hour, all the while knowing you're going to see them in 90 minutes, right? So it's not a waste of time to call this person up and get their estimate, but what you need to do is you need to correct it. You need to adjust it so that it represents the truth rather than the biased underestimation. We are going to do the same thing for sample variability. We're going to take the sample variability and we're just going to adjust it so that it becomes a true measure of population variability, and that's why the formula is different. All right, so some things stay the same. So for example, deviation is still the distance from the mean. This time it's the distance of each sample score from the sample mean. So it's your scores minus your sample mean. That is going to give us those deviations. That's going to give us these green distances from the sample mean. We are still going to have to square those deviations because deviations from a mean, add them all together, they always add up to 0. So we now square those deviations. We take our distances from the mean and we square it. So once again, scores minus the sample mean, all of it squared. So far looks exactly like the population steps that we did. Once we have all our squared deviations, it's time to sum them all up. And once again, this is exactly like what we've done for the population. And once again, we have the sum of the scores minus the sample mean, all squared, order of operations becoming very important. And once again, this is labeled sum of squares. This is labeled SS. And you want to read that as sum of squared deviations. It will oftentimes, once again, be labeled as sum of squares. Be very careful. Do not read it as SS. Do not read it as sum of squares. Remember those poor grad students, read it as sum of squared deviations. Train your brain because this is literally sum of squares. That's not what we want. We want that. So don't trick your brain into thinking this is what we're trying to calculate. Always call it the sum of squared deviations. And just so that you know, Excel is actually in on this possible conspiracy. I don't know. So we got to be doubly careful because it's just throughout statistics. I don't know if it's like purposely done to trip students up, but don't fall for it. Sum of squares, no. Sum of squared deviations, that's what we want. And once again, much like the population, you have a definitional formula that makes the sum of squared deviations much easier to calculate. And once again, we're going to use Excel. So where is the difference? Well, the difference comes right now. So we have our sum squared deviations. Now we're going to find our mean squared deviation, but this time we're going to divide it by the number of scores minus 1. And that minus 1 is the correction. That minus 1 is the adjustment of the bias. So we do the sum of squared deviations divided by the size of your sample, that small n, minus 1. And that minus 1 makes the final result bigger. You're dividing by a smaller number, so you can get bigger portions. So that sum of squared deviations divided by the size of your sample minus 1, that gives us sample variability. And then once again, sample variance. And then once again, we don't want variability squared. We don't want average deviation squared. So to get our sample standard deviation, once again, it's the square root of the sample variance. Sum squared deviations divided by the size of your sample minus 1, that correction for the underestimation, and that gives us sample standard deviation. All right, so any questions on that? Okay, so that was your peek behind the curtain so that we know what we're doing. What we're going to do right now is we're going to do some live follow-along demonstrations. So if you haven't already, in Canvas, open up week 3, class 2 practice. Not extra practice, but the practice one, we're going to do some standard work on standard deviations, calculating sum of squared deviations, variance, and standard deviation. All right, so the sheet that you're looking for looks like this. And let me just zoom in on that first question. Try that again. All right, already zoomed. All right, so this is our question here. So once again, we have 3 sets of scores, 3 sets of raw data. We have our X scores, our Y scores, and our Z scores. And what we want to do is we want to calculate and put into the answer cells here our sum of squared deviations, our sample variance, and our sample standard deviation. So I will show you the formulas for population variance and population standard deviation, but we're going to work on sample variance and sample standard deviation because, again, they're the more important ones. Okay, so the first thing I'm going to do is I'm going to show you what not to fall for. So don't do this with your Excel sheet yet, but this is the importance of knowing the difference between sum of squares and sum of squared deviations. We want sum of squared deviations. SS in your brain needs to read sum of squared deviations. Because if you go to Excel and you put in sum and then you start to spell squared, SQ, notice that Excel right there says to you, oh, you are looking for the sum of squares, right? I'm going to give you sum of squares. Returns the sum of squares of arguments. So even Excel is in on it. And it'll say, yeah, sum of squares, is that what you want? I'll do it for you. And this is not what we want. This is wrong. This is the sum of the scores squared. It has nothing to do with deviations. So again, train yourself. Because if you get to Excel and you're like, oh, I want the sum of squares, let me see, sum, oh, there it is. You'll make that mistake. And one of these semesters, I will get 100%. Nobody doing this error. I'm hoping it's this semester. So write down the one that we're looking for. We're looking for sum of squared deviations. That is DEV SQ. And you can see Excel right there. Once you ask it for the right thing, it's very friendly, returns the sum of squares of deviations of data points. That's exactly what we want. So we open up our parentheses, we highlight all of the X scores in this case, close those parentheses, hit enter, and you are going to get usually a very large number. Don't worry about that, because when we pop it into our answer cell using the equals function, so that we carry all those round off digits, and all the decimal points, we see that we have that one correct. So we'll do this one more time. So once again, equals DEV SQ. Highlight your Y scores in this case, close the parentheses, hit enter. We see that we have a larger sum of squared deviations for the Y scores. And then finally, we have equals DEV SQ for sum of squared deviations, open parentheses, highlight those scores, close your parentheses, and we have that for the Z scores, and we got that correct as well. All right, so that is sum of squared deviations. The next one we want is sample variance. So the first thing to remember is, in general, samples get English letters as their terms. Populations get Greek letters as their terms. So this is sample variance. If it was sigma squared, that would be population variance. So once again, I'm going to show you what not to do, because your homework will require this. So make sure that you write down this equation for your notes. The formula for variance starts off as var, and then if you want population variance, you want to choose the one that says .p. So .p is your way of telling Excel that you are doing population. The P stands for population. So you can see here it goes calculates variance based on the entire population. So that's what we would want if we were calculating population variance. But if you're calculating sample variance, just to illustrate this, notice that when we pop it into our answer cells, it's incorrect. So population variance, that formula will give you a very different number than sample variance. So be careful that you read which one is being asked for. On the exams, on these practice sheets, we are going to deal with sample variance and sample standard deviation, because that's the one that you're going to be using the most. In your homework, however, because of the way the textbook is structured, they don't highlight this distinction until later. That's one of the things I disagree about this textbook with. And your homework will ask you for population variance. So I'm showing you here how to calculate that using Excel. It's just that var.p, P for population, and use that for your homework. Now let's do this correctly. For the variance for a sample, you can use var.s. That is the newer formula for sample variance. But just to show you how important sample variance was, the original formula, which was just var, calculates sample variance. So even Excel realized that most people, 99.9% of the time, are going to be working with a sample. So just var, just variance, calculates the variance based on, if you look down here at the var one, this function is available, okay, for compatibility is backwards compatible, estimates variance based on a sample. So just var alone, and that's the one that we're going to use because it's the most backwards compatible, just var alone calculates sample variance. So you can use either one, var.s or just var alone. Just make sure that you're calculating sample variance, because now you'll notice the number is bigger. It used to be 857. The corrected one is 935, and now we've gotten that one correct. So once again, let's do this for y equals var, equals var, open parentheses. That is for your sample variance. Close those parentheses up and pop it into the y answer cell using equals function. And this is when it's getting especially important to use the equals function, because there are a ton of decimals here that we want to carry through with the rest of our calculations. So one more time, sample variance equals var, be able to type it one day. Equals var, open your parentheses, highlight your cells, close those parentheses. We hit enter, pop that into your answer cell using the equals function, and we got that one correct as well. All right, last one. We want sample standard deviation. This is much like var. It's one of the more friendly formulas. So sum of squared deviations, tricky. DEVSQ, that's one you're looking for. Standard deviation, very friendly. STDEV. So ST for standard, DEV for deviation. And once again, notice that we have that special population formula. So STDEV.P. Make a note of this. This is what you want for your homework. Your homework is going to predominantly ask for population standard deviation, population variance. So make sure when you're using Excel for your homework, you're putting in that .P. So var.P for population variance, STDEV.P for population standard deviation. We, on the other hand, are going to use the backwards compatible formula, STDEV, and that calculates sample standard deviation. So once again, notice even Excel knew this is the one that most people are going to use. The general formula for standard deviation calculates sample standard deviation. So STDEV, open those parentheses, highlight your scores, close those parentheses, and we see that we have a standard deviation for the X scores of 30.59. And notice that this is exactly the square root of the of the variance. So variance, standard deviation is the square root of variance. Variance is just your standard deviation squared. So that's the relationship between those two. So let's finish this off by calculating the sample standard deviation for the Y scores. So equals STDEV. Open those parentheses, highlight your Y scores. We have the standard deviation for those. For the Y scores, about 48.5. Pop that in using your equals function. You got that one correct. And then finally, we have for our Z scores, STDEV. Open your parentheses, highlight your scores, close those parentheses, and we have a standard deviation of 75.9. So notice here that we have discovered for our scores that scores on the Z scores are very widely distributed, right? There's a lot of difference between the scores on the Z scores. And if you take a look at the Z scores, you can see that we go as low as 4 and as high as 263. So on our Z scores, we are dealing with a lot of variability in our Z scores. Less variability, lower standard deviation for our Y sample, less variability, lower standard deviation for our Z scores. And you can see that the Z scores, they do have some small scores, but in general, they are in the mid 10s, upper 10s in terms of their scores. All right, so those are the three new functions I wanted to show you. So you have practice here. So you can practice your formulas, practice your copying and pasting. Now that you've seen the formulas 3 times each, you can go ahead and start copying and pasting those, practicing those skills. So we have an easy example of copy and paste, and then we have one where you have to practice your skills at making sure that your coverage and your formulas are set up correctly, and you have a few opportunities to do that as well. So that's the practice for the standard deviation. And we're going to open up practice time in just a moment, but just a few final things to take care of in terms of announcements for the class. All right, so we have our, that was our practice sheet. There's also an extra practice sheet, I believe, that you can work on if you've, once you've done this one as well, just to get that extra practice, get that extra facility and automatic nature. Remember, we are building the fundamentals here. We're going through that Karate Kid practice of wax on, wax off, because once we need to string it all together, you want to make sure that you're not having to think about it. So once we're starting to think about, and use sum of squared deviations, if you just know, oh yeah, DEVSQ, That's going to be a lot better and make it a lot more straightforward than if you have to sit there and go, okay, sum of squared deviations, not sum of squares, the other one. We're there right now. Make sure you put it into practice to get to where you need to go. Just a reminder for the pretest points, those you can again earn mastery points through the Quiz Me options. Through doing the pretest, post-test, and homework, you can also earn mastery points. And I will bump up your grade on the pretest for any chapter to whatever percentage of mastery points you have earned for that chapter. So you can bump up your pretest to 100% if you so wish. You have that option. Just to kind of put it on your radar, pretest mastery points are due the day before the exam. So they're due midnight before the day of the exam. So just be aware that if you are taking that option, that's when I'm going to download your scores. That's when I'm going to take a look at what you've achieved. So that's your deadline to earn 100% on your pretest. As I mentioned before, there is that extra practice Excel sheet, so feel free to work through that. And now you are finally ready. You are finally prepared for homework assignment number 3 and number 4. So these ones will have questions that ask you about measures of central tendency and about measures of variability. So they were lumped together, so you have to wait until today to get the sort of complete version of that. But just a final reminder, we in this, and on the exams, typically in class, we're going to be using measures of samples, so sample variance, sample standard deviation. However, at this point, your textbook has made the decision to just use the population versions of these equations. So when you're doing your homework, number one, make sure that you're using population variance and population, standard deviation. And then also, in your homework, make sure as much as you can, you're doing things in Excel. So there's ways of downloading and the scores into an Excel sheet so that you can have those in Excel. But even if you can't, I would say take the time, enter the scores into Excel, and use that opportunity to practice your formulas and your Excel skills. Because sometimes, the question might have 5 scores and say calculate the mean. And I know that you are probably going to be faster on your cell phone, opening your calculator app, just putting in those 5 scores and dividing by 5. It's probably going to be faster, but it's not going to build those skills. You want to make sure, just like Mr. Miyagi was making sure that Daniel was cleaning the cars with the right motion and not doing the ones that was not doing the motion that was faster, you want to make sure you're doing the same thing so that you can get that practice in. So as much as you can on your homework, use Excel, use the Excel formulas to do the calculations, and that'll go a long way towards building those skills. All right, so at this point, we got 20 minutes left in the class, so we're going to turn this over to practice time right now. So you have this opportunity to practice on anything that we've been working on so far. So even if you still need to do some of the order of operations, feel free. Excel sheets on the mean, Excel sheets on standard deviation as well. If you want to start up in your homework, give that a shot while I'm around in case you run into any obstacles. Feel free to do that as well. But, it is Thursday. If you've had a long week and you want to call it an early day, no judgment here, head on out. But if you do have any questions, call me over and I'll make sure that you get the help you need. Other than that, I'm done covering what I wanted to cover today.
So right now we're doing population, but we're going to do sample for the tests? Is that how it works?
Yeah, so the way that it works is that because populations are simpler to deal with, your textbook basically says, we'll start with population, we'll teach you the wrong way, and then we'll make a correction later. And I don't like that teach you the wrong way, so we're going to learn about samples from the get-go because I feel it makes the switch easier to make. Okay. But just so that you don't get frustrated, in your homework, at this point, we're doing, it'll be population calculations. The switch occurs, I believe, in chapter 6, is when they finally do it the right way. In any of these Excel sheets, we're going to be using samples, and then on the exam, we're also going to be using samples. So it's because honestly, you will never touch population data. It's even the census is technically not population data because as soon as you knock on one door and the person doesn't answer, you're not dealing with population. So that's what we'll be doing in this class.
Do we have to know the difference between population and sample stuff?
You mean like conceptually, like what? No, we in this course, the kind of general approach that I use is I give you a bit of background on conceptual stuff, but really it's geared towards performance.
Okay.
And what I kind of find is that if you understand it conceptually, you'll be able to do it. But if you don't understand it conceptually, you'll still be able to do it. And the doing it will eventually allow you to learn it conceptually. So the bottom line in this course is it's more important for you to be able to do it. So it's more important for me to be able to ask you, if you were in grad school or if I was an employer and I came up to you and I said, here's data, calculate the variability of this. It's more important that you say, okay, I can do it, rather than, oh, let me explain to you the difference between the sample and the population. So it's my experience that, and this is a good thing to keep in mind, even if you're kind of struggling with the peaks behind the curtain and exactly conceptually what is going on, everything that we're doing just kind of follows steps, right? And if you don't know kind of what's going on behind the scenes, at the very least, you can follow the steps, you can get the right answer, you can do statistics. And it's been my experience with just about every single student that if it doesn't come immediately, it'll come later. And at one point they're like, oh, I get it now. But the whole time they were able to do it.